Every electricity generation technology has advantages and disadvantages. For example, renewable technologies such as solar and wind do not produce greenhouse gases but are not always available when needed and can require significant amounts of land. On the other hand, technologies such as coal and nuclear can produce electricity in large quantities reliably around the clock but can result in significant greenhouse gases when unabated in the case of coal or long-term waste disposal considerations in the case of nuclear. Understanding these trade-offs among generating technologies reinforces the importance of having a diverse generation technology portfolio for reducing greenhouse gas emissions while economically and reliably meeting electricity demand. When applied as part of an integrated portfolio, all generation technologies can play useful roles that capitalize on their strengths. This video explores some of the advantages and challenges of both current and emerging electricity generation technologies when comparing attributes including cost, availability and operational capabilities, and environmental considerations. It presents a comparison of technologies at a high level, followed by a more detailed explanation for the assessment of each parameter analyzed for each technology. While the assessments represent the general characteristics of the technologies evaluated, the exact details of many parameters will be unique to the site, region, and/or country in which the technology is being considered. Furthermore, the details around the costs and capabilities of emerging technologies are less certain than those of generation technologies that have been mature and commercialized for decades and reflect expectations more than demonstrated capabilities. While the information included here can help to inform the planning and stakeholder engagement processes, more detailed analyses are required for making final investment and deployment decisions. One can see in this slide about all generation means from its advantage to challenges like its construction cost and electricity production cost along capacity factor. Ramping capability is a very important factor when choosing these generations in your network. Availability of these generation along total area use intensity along direct water use intensity. Comparison shows among all these generation type about direct greenhouse gas emission along direct emission, which is very important aspect tackle global warming issues on our Earth. Another important factor is direct waste products of these generation techniques along ease of permitting. Life cycle of any generation is also an important factor when considering. As conclusion, solar PV generation overall favorable in today's scenario as it has more advantage compared to other technologies where biggest factor is construction and electricity cost, but its availability is still a big challenge. Now we will talk about CCS, carbon capture and storage. CCS is a vital technology that plays a significant role in mitigating the impacts of climate change. As the world continues to rely on fossil fuels to meet its energy needs, the emissions of carbon dioxide and other greenhouse gases continue to rise, leading to global warming and other environmental concerns. CCS is a process that captures carbon dioxide CO2 emissions from power plants and other industrial sources before they are released into the atmosphere. The captured CO2 is then transported and stored underground in geological formations such as depleted oil and gas reservoirs or saline aquifers. This process prevents the carbon dioxide from entering the atmosphere, thereby reducing the impact of greenhouse gases on climate change. The technology behind carbon capture and storage is relatively simple. The CO2 is first captured through a process known as post-combustion capture, pre-combustion capture, or oxy-fuel combustion. Post-combustion capture involves capturing CO2 from the flue gases emitted by fossil fuel power plants. Pre-combustion capture involves capturing CO2 before the fuel is burned, and oxy-fuel combustion involves burning the fuel in pure oxygen to produce a pure stream of CO2. Once the CO2 is captured, it is compressed into a dense liquid form and transported via pipelines or ships to underground storage sites. These storage sites are carefully chosen to ensure that the CO2 remains trapped underground for thousands of years, preventing its release into the atmosphere. The benefits of CCS are manifold. First and foremost, it reduces the amount of CO2 emissions that enter the atmosphere, which is crucial in mitigating the impact of climate change. Secondly, it can be used with existing fossil fuel power plants, making it a cost-effective option for reducing emissions. Thirdly, it has the potential to create jobs and stimulate economic growth, particularly in regions with abundant fossil fuel resources. There are some concerns associated with CCS, however. Critics argue that it is expensive and that the technology is still in its infancy. Others are concerned about the safety of storing large quantities of CO2 underground and the potential for leaks. However, many experts believe that these concerns can be addressed through continued research and development. In conclusion, carbon capture and storage is an essential technology that has the potential to play a crucial role in mitigating the impact of climate change. By capturing CO2 emissions from fossil fuel power plants and storing them underground, CCS can significantly reduce greenhouse gas emissions and help to create a more sustainable energy future. As we continue to search for alternative sources of energy, carbon capture and storage is likely to become an increasingly important part of the energy mix. Emerging power generation technologies are new or innovative energy solutions that aim to provide cleaner, more efficient, and sustainable electricity. These technologies often incorporate carbon capture and storage (CCS) to reduce their environmental impact. Here's a brief overview of some of these technologies. Coal plus carbon capture and storage. When it comes to advantages, coal-fired power possesses irreplaceable capabilities in ensuring power system safety and grid stability when compared to renewable energy technologies. When it comes to challenges, high upfront costs, additional water requirements for chemical and physical processes to capture and separate CO2, potential groundwater contamination due to CO2 leakage during geologic sequestration, and severe resource constraints, especially water, in an era of global warming. Natural gas plus carbon capture and storage. When it comes to advantages, natural gas with CCS could be a critical technology to mitigate climate change while reliably delivering electricity. When it comes to challenges similar to coal plus CCS, it also faces challenges such as high costs, additional water requirements, potential groundwater contamination, and commercial challenges. Biomass plus carbon capture and storage. When it comes to advantages, bioenergy with carbon capture and storage captures CO2 emissions from biomass power plants and stores them underground. The main challenges include high upfront costs, location-specific constraints, and potential environmental impacts. When it comes to challenges, high upfront costs, location-specific constraints, and potential environmental impacts. SMR nuclear. When it comes to advantages, small modular reactors (SMRs) are a type of nuclear fission reactor which are smaller than conventional reactors. This makes them safer and more cost-effective, with less nuclear waste. When it comes to challenges, the main challenge is the potential for induced seismicity or human-induced earthquakes. Offshore wind. When it comes to advantages, offshore wind farms generate electricity from wind speeds that are typically faster than on land. When it comes to challenges, the main challenges are the high costs and difficulties in building and maintaining the wind farms. Solar PV plus storage. When it comes to advantages, this technology combines solar photovoltaic PV power generation with energy storage systems. When it comes to challenges, the main challenges include high upfront costs, efficiency losses during energy conversion and retrieval, and the need for large-scale and efficient energy storage solutions. Enhanced geothermal. When it comes to advantages, enhanced geothermal systems (EGS) are a new type of geothermal power technology that do not require natural convective hydrothermal resources. When it comes to challenges, the main challenge is the potential for induced seismicity. These technologies are still under development and may become major contributors to the global energy mix in the future. However, they also face significant challenges that need to be overcome.